In this segment, we're going to talk about the Fourier transform over the group of integers modulo n. Okay, the Fourier transform can be defined over any finite abelian group, and we've already been working with one example of the Fourier transform, which is just h tensor n. That's the Fourier transform over z2 to the n. For the period finding problem, we're going to be working with the Fourier transform over a different group, over the group of integers modulo n. And at a very high level, you can think about the Fourier transform is a change of basis that lets us see the pattern of a periodic function. Okay, and I'm actually going to describe the Fourier transform in a fairly general way here, so that you can see where it comes from. For any finite abelian group. And the way that we're going to do that is by talking about a function that's called a multiplicative character. Okay, so we will specify the discussion to the group of integers modulo n, but again, the definition of a multiplicative character holds more generally. Okay, so a multiplicative character over Zn is a function from Zn to the complex numbers that has the property that chi of x plus y is equal to chi of x times chi of y. Okay, so kind of multiplication of chi respects the addition of the group. Okay, so think about the case where n is just 2. So the group of two elements, 0 and 1, with addition modulo 2. So what would be a non-zero multiplicative character in this case? Okay, so basically what you need to define is, there's just two elements. So chi of 0 should be something, and chi of 1 should be something. Okay, so what can you plug in here so that this property holds? Okay, I'll let you think about that for a second. Okay, so the first thing to notice is, of course, we could just plug in 0 here. This is a very boring solution, and that's why we actually always exclude this case. So we talk about non-zero multiplicative characters. Okay, so we don't want that case. Okay, so what else did you come up with? Maybe you also saw this solution, right? We could make both of these 1. Okay. So we see that then this property holds, right? Because, chi of z in this case is always 1, and chi of x times chi of y, if these are both 1, will also always be 1. Okay. So this is called a trivial character, right, where chi is the constant 1 function. Maybe you also saw this solution where we can make this -1. Okay, so this works too, right? So let's just go through the cases. So of course 0 plus 0 is 0, and then I'm just going to look at, so if both x and y are 0, so this left-hand side is going to be chi of 0, that's 1, and chi of 0 times chi of 0 is also 1, and then if we have 0 plus 1, so that's of course 1. So now chi of 1 is -1, chi of 0 is 1, chi of 1 is -1. Okay, so that product is also -1, so that case works. By symmetry, of course, this case works as well. And we just have one more case to check. Okay, so in this case, chi of 0 is 1, and on the right-hand side, we have chi of 1 times chi of 1. They're both -1, so that would be 1 as well. Okay, so all these cases check out. Okay, so we found two non-zero characters. Okay, the trivial character, which always maps to 1, and this sign character where chi of 0 is 1 and chi of 1 is -1. Okay, so we found two non-zero characters over Z2. this trivial character and sign character. And notice that if we think about these as two-dimensional vectors, so we associate this with the vector 1, 1, and this with the vector 1, minus 1. Okay, then if we make a matrix whose columns are those characters, okay, and appropriately normalize it, then we end up with the Hadamard matrix. Okay, so that's why the Hadamard matrix is an example of the Fourier transform. Okay, so now we want to figure out what the multiplicative characters are over Zn. Okay, and we're going to do this just by figuring out what some general properties that a non-zero multiplicative character over Zn must satisfy. Okay, and the first property that we see is that if chi is a multiplicative character, then chi of 0 must be equal to 1. Okay, so why is that? Well, x, of course, is equal to x plus 0. So if chi is a multiplicative character, that tells us that chi of x plus 0 is equal to chi of x times chi of 0. And now this should hold for any chi of x. So in particular, if this character is non-zero, there must be some x for which chi of x is non-zero. Okay, so if chi of x is non-zero, then we can divide by chi of x, and we find that chi of 0 is 1. Okay, so that's our first property. Okay, let's move on to the second property. Now let A be an arbitrary element of Zn. Now we can write A just as 1 plus 1 plus 1, A many times. Okay, so now if we inductively apply the character property to this sum, we see that chi of 1 plus 1 plus 1, A many times, it's equal to chi of 1 to the power A. Okay, so this tells us that a character is actually completely determined by chi of 1. Okay, now we know that for every A, chi of A is equal to chi of 1 to the 8th power. Now the next property that we see is that chi of 1 to the power n, again we're working modulo n, has to be 1. Okay, so why is that? Well, if we sum up 1 n times, that's just 0 modulo n. So this is equal to chi of 1 to the n. On the other hand, it's also equal to chi of 0, which in the first property we saw is 1. Okay, so that means that chi of 1 is an nth root of unity. Okay, so now we know that for any character chi of 1 has to be an nth root of unity. All the other chi of A, they're just powers of chi of 1, so they're also nth roots of unity. Okay. Okay, so now if we let omega be e to the 2 pi I over n, so a primitive nth root of unity, we can define n different characters just by what we set chi of 1 to be. So if we define chi A of 1 to be the 8th power of this primitive nth root of unity, then we get n different characters. Okay? Okay, so let's just explicitly check that this definition works. Okay, so if we look at chi A of x plus y, so that's just omega to the A times x plus y. And now distributing here, this is omega to the ax times omega to the ay, which is indeed chi A of x times chi A of y. Okay, so this definition here does indeed satisfy the property of a multiplicative character. Okay, so we're going to be working a lot with these characters, figuring out more properties that they have. So it's useful to develop some identities we can use when we're manipulating them. Okay, so the first thing that we see is that you can actually exchange the name of the character and the argument. So you can exchange the subscript here and the argument. Okay, because chi A of x, that's just omega to the A times x, which is also equal to the the xth character evaluated at a. Okay, so we can always exchange the argument and the subscript. So here's an example of how you can use that. If you have two different characters, potentially different characters, chi A and chi B, and you multiply them, evaluated at the same argument, then I can exchange the argument and subscript. Okay, so I can view them as the same character evaluated at different points. Then I can use the multiplicative property, okay, and then I can exchange the argument again. Okay, so this tells us that chi A of x times chi B of x is actually equal to chi of a plus b evaluated at x. Okay, so this says that the characters themselves under the operation of pointwise multiplication form a group that's isomorphic to Zn. Okay. Another thing that we're going to need to do is look at the complex conjugate of a character. Okay, so again, using the property of being a multiplicative character, we know that chi A of x times chi A of minus x should be the same as chi A of 0. So in the first property, we saw that that's just 1. And we know that chi A of x is a root of unity. So that means that chi A of minus x must be the complex conjugate of chi A of x. Okay, so that's written here. Okay, so we will make use of that property as well. Okay, now we come to the key property of characters. Okay, so this is really important because this is the reason why Shor's algorithm works. Okay, this is why the Fourier transform is so useful to tell us information about the period of periodic functions. It's also the reason why the Fourier transform is a unitary operation, and therefore we can make use of it in quantum algorithms. Okay, so this is a very important. This is kind of the key lemma that makes a lot of things work. Okay, so let's go through this. So let chi be a multiplicative character. Suppose that r divides n, and that chi of r is not equal to 1. Okay? Then if you look at the sum over all a that are 0 mod r of chi of a, that sum is 0. Okay? So this is our key lemma. And just to get some intuition for what's going on here, the idea is if we look at this set R of all things that are 0 mod R, well, this set, it's kind of well spaced. So if we look at e to the 2 pi I a divided by n for a and r, these vectors are kind of well equally spaced around the unit circle here. Okay, so they kind of balance each other out, and when you sum them up, you just get 0. Okay, so let's see why that's the case formally. So again, let's let R be the set of A, which are equal to 0 mod R. So the key fact here is that if we translate the set, capital R, by little r, we just get back to the same set. Okay, so the notation that I'm using here, so what is, R is just a number plus a set. What does that mean? Well, it's again a set, and you take everything in R, capital R, in the set, capital R, and add little r to it. Okay, so if we look at this set, you see that this set is again just equal to capital R again, right? Because everything in here is still going to be 0 mod little r when I add r to it. Okay, so basically, adding r to everything in this set, the set is invariant under that operation. Okay, so doing that doesn't change the set. And that's really the property that makes this lemma work. Okay, so let's see why. Okay, so let's see. let's start actually here on the right-hand side. Okay, so this is the quantity that we're interested in, sum over A and R, chi A of R. Now, by this property, the fact that translating the set by R doesn't change the set, so summing over A in capital R is the same as summing over A in R little r plus R, okay? Now let's think about this for a second. So if you're in this set, right, then you're basically of the form little r plus something in capital R. Okay, so we can again, so again we know that chi of little r plus a from the multiplicative property is equal to chi of r times chi of a. Okay, so that means that this sum here is going to be, I can pull out this factor of chi of r, which is going to appear in every term. So this is equal to chi of r times the sum over a in capital R of chi of a. Okay, so now you see that I have that chi of r times this sum is equal to that same sum itself. Okay, so now if this sum is not equal to 0, then I could just divide by this sum, and I would find that chi of r is 1. But I'm promised that chi of r is not equal to 1. Okay, so therefore, this sum must be equal to 0. Okay, and that proves the lemma. Okay, so let's see how this lemma gives us a very important property of the characters, and that is that they are orthogonal. Okay, so let's look at the dot product of two characters, chi a and chi b. So this is the sum over all x, chi a of x complex conjugate times chi b of x. So now I'm again going to use a couple of our properties. I'm going to switch the subscript and the argument, and I'm going to use that taking complex conjugate is the same thing as negating the argument. So that's what I've used here. Now in this step to this step, I'm using the multiplicative property, okay? And now I'm exchanging the subscript and argument again, okay? So I arrived at this inner product is the same as the sum over x of chi of b minus a of x, okay? Now I'm summing over all x and zn, and you see that this is a special case of the previous lemma. So it's basically like where we're using the set R is the set of all A such that A mod 1 is equal to 0. Mod 1. Okay. Okay, so we can apply the previous lemma as long as chi b minus a of 1 is not equal to 1. Okay? Okay, so we can apply the previous lemma as long as chi of b minus a of 1, because we're looking mod 1 here, is not equal to 1. Okay, and this will hold as long as b minus a is not equal to 0. Okay? Okay, so as long as b minus a, which means that, as long as we're not taking the same character here, this dot product is going to be equal to 0. Okay? If we take the same character, then we're looking at chi of 0 here, and chi 0 of x is always 1 for any x. So in that case, the sum will be n. Okay? So basically what we've shown here is that distinct characters are orthogonal, and the L2 norm squared of a character is capital N. Okay? So what that means is that if I take the characters and I put them as the columns of a matrix, and then I normalize things by 1 over square root of n, then this matrix is going to be a unitary, okay? Because the columns of this matrix form an orthonormal basis, okay? These normalized character vectors. Okay, so now we're very close to the Fourier transform. Okay, let's just remember what we said initially the Fourier transform was. So the Fourier transform is the change of basis matrix from the standard basis to the normalized character basis. Okay, so what does that mean? That means that the Fourier transform, Fn, is the matrix that takes a vector f to a vector f hat, which represents f in the character basis. Okay, so more precisely, f is equal to 1 over root n times the sum over a, f hat of a times chi of a. Okay, so these coefficients here, they're multiplying the characters to give us f. Okay, so it's just how to write f in this basis of normalized characters. Okay, so let's think about this equation for a second. And we can write this more succinctly in matrix notation. So if we take the matrix from the previous slide, U, the columns of U were exactly these normalized characters. Okay, so that means that U times f hat, what is this? U times f hat, it's just going to be a linear combination of the columns of U with the coefficients in that linear combination given by the entries of f hat. Okay, so it is exactly what we have here on the right-hand side. Okay, so we can just more succinctly write this equation in matrix notation as f equals U times f hat. Now again, what are we after? We're after the matrix Fn, such that Fn times f gives us f hat, right? So it gives us these Fourier coefficients, how to write f, the coefficients that tell us how to write f in the character basis. So if we just look at this equation here, and we multiply both sides by the conjugate transpose of f, then we have U star U f hat. Okay, but this is just the identity, right? Because U is a unitary. Okay, so this U star here is exactly the matrix Fn that we're after. Okay, so U star is the Fourier transform matrix. Okay, so U star times f gives you the Fourier coefficients and tells you how to write f in this basis of normalized characters. So let's take a closer look at Fn. So again, what is it? It's the conjugate transpose of the matrix whose columns are the normalized character basis. So that means that the rows of Fn are going to be the complex conjugates of our characters. Okay. So here's what Fn looks like by rows. We're also going to need to know what Fn looks like by columns. Okay, so if we just look at the jth column of this matrix, then, well, what is that going to be? Well, it's going to be this, right? Chi0 star of j, Chi1 star of j, etc. And again, taking the star is equivalent to negating the argument. So that's equivalent to this. And now we can exchange the subscript and the argument. So it's basically the character labeled by minus j. So the jth column of this matrix is the character labeled by minus j, normalized. Okay, so that's how to think of it by columns. We can also just think of it by entries. Okay, so the j comma k entry of the Fourier transform matrix is going to be omega to the minus j times k divided by root n, where again, omega here is our primitive nth root of unity. Okay, and this matrix U that we kind of first talked about, that's the inverse Fourier transform. Okay, so it changes from the character basis to the standard basis. So its columns are just the normalized character vectors. Okay, so here's an example with n equals 6. So I guess it's probably easier to think about the inverse Fourier transform first. So its columns are just the characters here. So here, in the first column, the entries here are powers of omega to the 1. Here they're powers of omega to the 2, powers of omega to the 3. Okay. And then you just take the conjugate transpose of that matrix, you get the Fourier transform matrix, which looks like this. Okay, so a couple notes about our presentation. So our definition of Fn is what's usually called the discrete Fourier transform in the classical literature. So the normalization might differ than what you see in the classical literature because we want things to be unitary. But basically, in classical literature, the Fourier transform is the matrix that transforms you from the standard basis to the character basis. So for some reason, in quantum computing, the quantum Fourier transform is usually defined to be the inverse of the Fourier transform in the classical literature. Okay, so it's a matrix that's taking you from the character basis to the standard basis. Okay, so it doesn't make too much of a difference, but that's just something to be aware of.